applications that meets the demand for diverse operating systems and middleware. It is not just one middleware. And look at the different options that we have for the middleware. And take a closer look at Adaptive AUTOSAR and AOS, compare them, and then present a case for coexistence of two platforms in the context of STV, and then present a solution with one case how we can actually bridge the gap between these two platforms. So yeah, before going into this slide, I think we all know that automotive industry is rapidly moving towards software-defined vehicles, and these software-defined vehicles, the cars are gradually transforming from electromechanical terminals to the more software-centric, highly intelligent, highly connected mobile devices. And in this software-defined vehicles, the architecture of the vehicle also is evolving. So here we see, this is the architecture in the past. This is how the vehicle architecture looked like. So we had separate ECUs for specific functions, limited functional integration, and the architecture was based on the CAN, FlexRay, and LIN network. So this was the backbone, and the model, it was based on the hardware-centric system integration. From this, we moved to the domain-specific controllers, where OEMs started consolidating the functions of one domain into one single controller and call it as domain controller. So we started consolidating the vehicle function so that we reduce the number of ECUs and reduce the complexity of connections. This was called as domain control architecture, and from here now we are moving towards this phase where we are trying to consolidate all the ECU functions, even the domains, into one central compute. So this is based on centralized compute-based zonal controller, where we have all the powers aggregated into one single computer, one or two single computers. This is domain independent controller. It has every function. There is no segregation based on the domain. And this is what we are currently looking at, the network architecture. So we will look at, this is network architecture, we will look at the software architecture, how it looks like. So if we zoom into this part a little bit, maybe we can. So this is how it looks like. These are the different operating systems that are part of the typical SDV. A typical SDV has all these different operating systems and middleware, because there are different domains, and all these different domains have different requirements. The requirements are different, and therefore we cannot have one single middleware and serve every application. So for example, for IVI apps, one of the famous operating system is AOS, the middleware, and for ADAS, body control or vehicle control applications, we have Adaptive AUTOSAR based middleware, and for the zonal ECUs we have Classic AUTOSAR, and for the end ECUs we have Classic AUTOSAR or a proprietary operating system or middleware from the OEMs. So this is how a typical SDV software architecture looks like, which consists of heterogeneous operating systems. Every OEM is talking about moving towards one common vehicle operating system, but we have not reached there yet. We still need a lot of different kinds of operating systems to meet the different domain requirements. And we will take a closer look at AOS and Adaptive AUTOSAR, compare them, and then see the coexistence. So this is just a slide which compares two middlewares. In terms of real-time capabilities, Adaptive AUTOSAR supports real-time requirements. However, AOS may have some limitations in this case. Coming to functional safety, it supports high ASIL standards, and it is suited for safety-critical applications. AOS is suited for user experience-focused applications. And the ecosystem Adaptive platform, it is based on the standardized automotive ecosystem, while AOS, it has rich application ecosystem. And the community collaboration. Adaptive AUTOSAR is based or driven by consortium, and the key players here are OEMs and the suppliers. AOS is driven by Google and open source community, which has rich developer community. If we have to interact with the deep embedded vehicle network, adaptive AUTOSAR can interact or it integrates seamlessly with the deep embedded vehicle network. But AOS has limitations in this area. So for applications of AD/ADAS, body, comfort or vehicle controller, adaptive AUTOSAR is more suited. And for in-car entertainment, smartphone integration, connectivity and communication features, AOS is more suited. Yes. So this is the important slide which I wanted to highlight today. We definitely need multiple operating systems or middleware. AOS for IB apps, adaptive AUTOSAR for AD/ADAS, body or vehicle control apps, and then classic AUTOSAR for the zonal, and we have the smart sensors here. So if we look at the right hand side of the ECU or the architecture, all these ECUs are based on mostly AUTOSAR standards. They are based on AUTOSAR standards and they are well integrated. There are few challenges while we were moving from this to this, where we were all signal based in the past. We moved to SOA. So there were some challenges, but there was a presentation yesterday on signal to service, which talks about how to get around this challenge and integrate these two issues. So in short, all these issues interact with each other well and they are well integrated. However, if we come to the left hand side, these two operating systems or middleware, there is a break in the software architecture here. They are based on two different standards. One standard is, one of the middleware is based on Google standard and one of the middleware is based on the consortium standard, Adaptive AUTOSAR consortium. And they both follow different rules of how applications are developed or designed or how applications communicate with each other. So there is a break in the software architecture, and if we have to write some applications or create digital services based on IVI, which needs to interact with this HPC over here, which is based on Adaptive AUTOSAR, developer community faces challenges. We cannot seamlessly interact with this HPC over here, and this is what we wanted to highlight. We want to bridge this gap, and not just in terms of communication, but in terms of deployment of the applications, in terms of diagnostics, logging, and software update. All these cases, these two operating systems behave completely differently and do not maybe follow the same standards. So we will take few cases, or let's look at why do we need this interaction between these two, or integration between these two operating systems. So what happens if we have a bridge between these two operating systems? We end up, we open a lot of opportunities for creating new digital services based on the IVI. And IVI system can interact or collect the data that is present on the AD/ADAS system, and also it can utilize the services that are present on the AD/ADAS system. So interoperability between these two platforms enables possibility of more advanced features and more monetizable features. One of the example is let's consider the example of DMS. We can have an application running on IVI system and it can use the DMS camera for video calls. This is one of the cases. So any developer, the IVI side, we have rich developer community and they can create more services if we enable access to the entire vehicle. So this is one of the cases. we can create more digital services and unlock the power of true SDD by bridging that gap between these two operating systems. So I'll call my colleague over here who will take us through different challenges we face and then a solution for it.
Yeah, thank you, Ilva. Right, so like Ilva explained, there are a number of challenges when we try to integrate adaptive AUTOSAR with other platforms like Android Automotive. An example, we will look at a few of these challenges and potential solutions for them now. Yes, here on the left side, we can see a number of challenges, like interoperability is a big challenge, of course, right? Because both systems use different communication protocols, right? So there, one of the potential solutions is the use of standardized interfaces, middleware solutions, frameworks, and protocol bridges to bridge the gap between, in example, the adaptive AUTOSAR side is often using some IP as a protocol, while we see on the Android Automotive side gRPC over vSOC. There is maybe now also some IP implementation, but exactly for this purpose, some middleware to bridge this can address this problem. Another area is the timing requirements are conflicting, right? For adaptive AUTOSAR, we have maybe near real-time requirements, while for the Android side, it is more on the infotainment side or telematic side where we don't have so strict requirements. So there are two cases. Adaptive AUTOSAR running on the same HPC as Android, or both running on different PCs, right? So if they are running both on the same HPC, the priority inheritance or priority ceiling mechanisms can be used, where if a high priority task is in process, if a low priority task is in process, it becomes high priority for a short time if a high priority task needs the same resource, in example, right? And in priority ceiling, there is a maximum defined by resource. What is the maximum priority a process accessing this resource can get? Another mechanism is time division multiplexing, where a certain time window is being defined. Maybe similar in FlexRay or other communication protocols, where one resource is for a certain time window only accessible for one VM. Right? Another challenge is the resource contention, right? Where quality of service mechanisms can be used, traffic shaping or policing if both are on different HPCs, then this can be configured in the switch, or bandwidth allocations to prevent network congestions between the two VMs. One more integration challenge is security, right? Where, of course, both VMs are segmented and isolated. Secure communication can be used, in example, some IP with authentication. Intrusion detection, intrusion prevention systems can be deployed and configured to detect anomalies in the communication. And of course, software updates need to be installed timely to ensure that vulnerabilities are fixed and non-vulnerable versions of libraries being used. Right? The last of the challenges here is diagnostics and maintenance, and that's what we will look at a little bit deeper now, where the diagnostic requirements, especially in the context of SDV, where it's not only classic diagnostics but also diagnostic of software, is very important. It's important to have there a unified framework, right? We don't want to have one diagnostic tool for Android, one for adaptive, or it's important that these are unified so that tester application, an example, doesn't need to worry about is it an adaptive platform or is it an Android platform. Right? And one solution for this area is specifically, we will look at a little bit more detail now. Yes. So here on the left bottom, we can see the vehicle with the gateway module, which is running hypervisor and different VMs in this example. In example, one VM running adaptive AUTOSAR and one VM running Android Automotive OS. Now, to diagnose these two VMs, we have here on the right side this SOBD VM, which can be again run on an adaptive platform, in example. But the that is that this VM implements a mechanism to abstract the communication protocol to adaptive or to Android, so that it can communicate to both. SOVD is service-oriented vehicle diagnostics. That is an ASAP standard. I think an ISO standard is also under development for that, which specifies an HTTP REST API as a diagnostic interface to the ECU, so that a tester can use this REST API and diagnose different ECUs, regardless if they are adaptive AUTOSAR, classic AUTOSAR, Android Automotive, or anything else. So here you can see this platform adaptation layer, which will abstract these low-level details about the communication protocol. In example, in adaptive AUTOSAR adapter, it might use some IP to capture log information from an adaptive AUTOSAR VM. While on an Android Automotive OS, it will use gRPC over vSocket to do the same, in example. And the same is possible for all other platforms, as example, Eclipse SDVU protocol. Right? It's one other way that could be used to capture the software diagnosis information from other VMs. Right? And at the same time, just integrating these two is not enough in a modern SDV vehicle, because we still have the legacy ECUs and the zonal ECUs. Right? So for that purpose, there's one more VM, this CDA VM, you see here, Classic Diagnostic Adapter, which can be implemented in many different ways. One way that we see on this slide shows a normal, traditional off-board diagnostic stack based on ISO standards that could be deployed in vehicle to do the same thing an off-board tester normally does, but in vehicle. That means interpretation of signals, translation from UDS to services, more or less. Right? That can be based on standards like OTX, ODX. Of course, this could be potentially being translated to something more performant for in-vehicle, right? So it doesn't need to be plain XML data or something like that. But it just shows the overall system will allow OEMs to use their existing diagnostic data they have from their off-board diagnosis tool, the existing diagnostic sequences they have from their off-board diagnostic tool, and deploy them in vehicles to execute the same use cases to capture information from these classic ECUs via UDS. Right? So that is the idea of such architecture. Right, and that is just an example, so it doesn't need to be exactly like that. It's just one of the possible solutions how that can be addressed to abstract the one-time adaptive AUTOSAR or Android OS away from the diagnostics. Right? We will look at the logical connection of such a setup here. That is similar to what I explained already. So we have the SOVD server, which is reachable via HTTP REST API, and then talks to different applications, which can be different VMs. Like you see here, we have adaptive AUTOSAR VM, Android Automotive OS VM, and one more VM, which could be again adaptive AUTOSAR, running the classic diagnostic adapter as an application, which will then talk to the zonal ECU, in example via UDS on IP via DOI, and the zonal ECU could translate that to UDS on CAN, or it could be directly UDS on CAN. It depends on the architecture of the OEM, but I think you get the overall picture of how the information would flow in such an environment. So to summarize a few important considerations when planning an architecture where adaptive AUTOSAR and Android is coexisting, utilizing a hypervisor to isolate these two if they run on the same VM. I think that's a very natural thing. Important is when designing the services and APIs to use an abstraction and not designing them based on a specific communication protocol. I think we saw today some interesting talks about using Flanker IDL to define that in one abstracted and not in the AIXML. It's either for adaptive or it's for classic, and even based on the version of the standard, the AIXML format differs, right? So defining the services in a platform independent way is one very important thing when planning these interactions between Android, adaptive, and potentially other platforms. Middleware solutions can really help here a lot to do translation from protocols, to integrate these ECUs, to integrate these runtimes better together. And the last 2 points are harmonizing of the logging and synchronization of timestamps, which is very important when looking at the diagnosis of software, where maybe we have an error potentially involving multiple VMs. We have to correlate timestamps and log messages to really analyze an issue or root cause, right? So that's where these 2 points are very important to do the efficient software diagnosis in such a system. Yeah, I think that is the last slide I had. Any questions?
Thank you very much, both. Okay, welcome.
Yes, thank you very much. I have a following question. So you mentioned coexistence of Android and AUTOSAR adaptive. Do they coexist inside vehicle on different ECUs? This is a problem, or it's also might be a case when they coexist on the same ECU?
Correct. So both are potentially a problem. So we see both cases on the same HPC running in different VMs, or in some architectures we have multiple HPCs where on one Android is running on one adaptive. Dilapa, do you want to add something?
Both cases are possible. I mean, in future we are seeing, okay, bringing everything onto one SoC and have hypervisor, so that you reduce all the wiring harness that is required. Now the wiring harness is reduced to just a middleware communication technology. If they are lying on different ECUs, we are bringing in a communication technology which is based on some bus. But when we put them together, now it all reduces to the operating system or the middleware layer. And that's where we need to bring in the intelligence, or that's what is called as the vehicle operating system, which all, I mean, automakers are going to use, or that's the direction.
Just a very quick question. Did you mention an example of coexisting AUTOSAR adaptive and Android on the same ECU? Or can you make an example of this kind of ECU?
These are under planning, yes. They do not exist, but yes, that's what.
Potentially they can.
Yes, yes.
Okay, thank you very much.
Thank you very much. So the last question.
Thank you very much. So you say that coexistence of Android and AUTOSAR. So I would like to understand, is there any augmentation or support from AUTOSAR planned for getting certification of Android Auto?
From the AUTOSAR?
Yeah. So basically, as the earlier question was that which issue I can think of infotainment issue, Android Auto and CarPlay is a use case. So Android Auto requires a certification, right from MFI. So that is a long overhauling process. So is there any augmentation support from AUTOSAR body also in that context?
I don't think so. There is no such support for certification from the AUTOSAR.
So basically it will again lie with OEM and Tier 1.
Yes.
Right? Thank you.
Because the OEMs are adding the additional features called as vehicle abstraction layer, VHAL layer, which is part of the AOS. The AOS which is shown here is very abstract, just one layer. But when we see a deeper look, then it has so many layers, and one of the layers which is vehicle abstraction layer, which is for that layer, only Android defines only the top layer APIs, the upper APIs which is based on AIDL. But the internals, how we connect this vehicle abstraction layer to the entire vehicle, it depends on the OEM.
So basically it's a stack handling only.
Sorry, unfortunately the time has come. Sorry. Thank you very much for both from the KPIT.
Thank you.
Thank you.